Good afternoon, ladies and gentlemen. I'm going to be talking about a good old civil engineering material, concrete. First of all, I'd really just like to give a little background to the problems with the concrete infrastructure, and then just looking at some work that we're doing on particularly monitoring concrete infrastructure. So just to give you some idea of the scale of this, the problem, as far as infrastructure is concerned, we have got a deteriorating infrastructure. And just to give you, some indication of the scale of things here, approximately 50% of the construction budget is spent on the repair and maintenance of existing infrastructure. And then with inspection and maintenance forming a major part, particularly with reinforced concrete structures, a major part of that, sort of 50%, is related to reinforced concrete. Again, just putting this in perspective, in this country alone, we're talking about £500 million worth spent on the repair and maintenance of reinforced concrete structures. Now, this is not just confined to this country. If we scale that right across the globe, we're talking of a multi-billion-pound problem. And also, there are these hidden costs. There are hidden costs in there, such as hidden costs caused by traffic delays. When we have a road closure, there is a cost associated with that. Particularly, there are economic costs and there are health impact problems as well, with things like road closures, which are required for carrying out maintenance on bridge and highway structures. I thought this was quite a nice quote here about, which I extracted, about timely maintenance activities which are well planned and carried out with minimal disruption to road users can present substantial savings in terms of time and money. So what I'm trying to sort of say here is, if we can get us some indication of how the structure is performing over its life, we can then have, say, timely maintenance interventions to go in and undertake some minor repairs rather than waiting for some major structural repairs. Again, this is a classic case of problems with reinforced concrete, and it's particularly the use of de-icing salts that we use on roads for winter maintenance purposes. That gets down, that's washed through the joints, it gets into the crossheads, gets into the bridge piers, and we can have some quite serious problems. So we don't want it to get to this state where people are losing their lives. So it is a major problem. That's what I'm really trying to emphasize here. And again, as far as the structure is concerned, we have got these different impacts. It's got societal impact, it's got an environmental impact, and it's also got an economic impact. Economics is a main driver, of course, but we must be aware as engineers of these other impacts, particularly environmental impact, not only with the initial construction, but also over its design life, particularly when we have to go in and do routine maintenance on the structure. Again, so I don't know whether you're aware of this de Sitter's law of fives. Now, whether it's the law of fives or a law of fours or a law of sixes, the point that's been made here, if we can go in and do some minor repairs, it's going to cost a lot less than waiting for a major repair. So, so really, basically, the longer you defer things, then the more costly it's going to get. So that sort of puts it into sort of an economic perspective as well. And as far as reinforced concrete is concerned, one of the major problems with it is, first of all, ferrous reinforcement. We use steel reinforcement, but also what protects the steel from the outside environment is this concrete cover, this thin skin of concrete, which protects the steel from the outside environment, is a major problem. So if we had some indication of what's going on in that region, I think we're stuck with ferrous reinforcement for the time being. Admittedly, we can have stainless steel, but that is quite expensive. So this concrete cover zone is quite important as far as the deterioration of reinforced concrete is concerned. So the corrosion protection, that's one of the main problems with reinforced concrete, protecting the steel against corrosion, against all the nasties that the environment throws at it. As far as corrosion protection is concerned, that cover zone, the quality of that cover zone is very important, and ensuring that we get the required quality in situ as well. So as far as these deterioration processes, and again, I'm sure many of you will be aware of these, but to the left, I've got the outside environment, and in the right, I've got what happens inside the reinforced concrete, where we've got maybe a 50, 60, 70 millimeter covering to the steel, and that's all that protects the steel from the outside world. Nature is very perverse. It's trying to change things. We've got that cover zone is subjected to cyclic wetting and drying. There's carbonation, that's the diffusion of carbon dioxide, atmospheric CO2 into the concrete. There's things like chloride ingress, not only from the marine environment, but also, as I've alluded to, de-icing salts that we use on roads for winter maintenance purposes. And there's things like sulfates as well from groundwater. What we're interested in, the properties that we're interested in, is not strength per se, as far as the cover zone is concerned. We're interested in these, what we call transport processes. We're looking at things like diffusion, permeability, and the absorption properties of that concrete cover zone. So these are the important parameters, and say not strength, not necessarily strength, although we do tend to be consumed quite a lot with strength. And as far as the environment is concerned, we're dealing with a very complex problem here. We can look at environment on different length scales. We could look at it on a regional level. The environment in the north of Scotland is quite different from the environment in the south of Italy. So we can look at it at that level. We can come down a couple of orders of magnitude, and we can look at I've called it a meso level, a local level, just looking at the individual structure itself. And that's got its own environment, but then we can take it even further and look at right down at what I'll call a micro level, almost on a surface level, because even within a structure, you get different environments, even within a structure. We've got vertical members, we've got inclined members, we've got horizontal members, we've got north-facing members, we've got south-facing, and so on and so forth. So it is a very complex problem that we're dealing with. And again, if you just go into the Euro codes, or the codes now that have been adopted, long gone are the days where we just had literally a handful of environmental descriptors for the old CP 110 or BS 8110. We've now got a range of environmental descriptors, 18 in all, within the new Euro code, simply because we've got this real problem with the deterioration of reinforced concrete. And as far as these transport properties are concerned, again, what we're looking at is the porosity of the material. We're looking at things like the pore size within concrete, looking at the cementitious material, looking at pore size distribution, looking at microcracking, and looking at the cement aggregate interface zone. Another important one there, that bullet point at the end, looking at hydration. Hydration, well, when you add water to cement, within 24 hours, it's turned from something that's liquid into something that's solid. But the properties they're time dependent. Cement is constantly hydrating. The properties change with time. So what we get at 7 days is going to be different from what I get at 28 days, which is going to be different from what I get at 1 year. So this constant monitoring really is important, and particularly with the amounts of pozzolanic materials that we're now using. These are now routinely specified. Ground granulated blast furnace slag, fly ash are used now routinely in concreting operations. So these properties, say, change with time. So it is important to monitor with time. And again, that's just look what the microstructure of cement looks like. This is what we're dealing with right down at the microscopic level, where we're dealing with pores and looking at this porosity of the cement. And again, we've got this other issue of, is what we get from our lab test, is that what we get in reality? If we had done pre-qualification and some pre-construction identity test, and if we had passed our concrete on that, is that actually what we get on site? Is that what we get in the structure? So there's this problem that what we deal with in the lab may not be what we get in the final structure, because the final structure is subjected to all sorts of environmental actions. So that's really sort of setting the problem. So as far as the service life of a structure is concerned, it depends on the penetrability, the permeation properties of that concrete cover zone. An important phrase there, as achieved in the final structure, not in the lab, but in the final structure. And also, if we take measurements on the final structure, then it actually is quantifying as I've said here, the result of all the people in the construction chain, from material suppliers, contractors, right up to specifiers and owners. So taking measurements in the final structure, say, quantifies everyone in this supply chain or construction chain. Again, I won't go into all the details here, but the point I'm thinking about or trying to put across here is that as far as structures are concerned, we really want to look at monitoring structures from day one. So we start at day one, so we're then able to build up an indication of how that structure is performing, how it's behaving. So we're looking at installation of monitoring systems within the structure. And that has to really start right at the design stage. It's not as an afterthought, it has to be thought of at the design stage. Now, many structures maybe don't need installation of monitoring systems, depends on the level of monitoring that you want. But it's best to get in there right at the beginning. And then, of course, any construction, there'll be a maintenance element to it. And again, these monitoring systems can give us feedback into how the concrete, how the material, how the structure is performing. So again, these integrated monitoring systems for both new and existing reinforced concrete structures do give us a more rational approach to repairing. We can schedule repairs based on feedback from these monitoring systems. And again, if I'm looking at the service life of the structure, how we define end of service life is another point for debate, of course. But what we're saying here is on the vertical axis we have got deterioration, however we want to quantify that, and along the horizontal axis is time. So we've got this sort of initiation period, and then we've got a period where perhaps we're talking about corrosion, looking at corrosion damage, where we end up with corrosion. We're talking about cracking and spalling of the concrete, and if we define that as end of service life, well, that is further along to the right there. So we've got this. What I'm trying to say here is, at this stage, we should really be looking at monitoring and testing, giving us constant feedback on how the structure is performing. So again, it'll allow us to go in and do maintenance interventions in a more rational way. And that's really what line 3 is there. We can have some minimum acceptable level of performance, and then over the service life, we can go in and do a number of maintenance interventions in a more rational way. Again, I do apologize for this. This is the only slide I've got with some equations. It wouldn't be an academic seminar if I didn't put a few equations up. But the point I'm going to make here is these properties, permeability and diffusion, and I've got in here the bottom one, the electrical conduction, they're all based on the same equation, really. So what we're doing in our work is measuring the electrical properties of concrete, the electrical conductivity of concrete. And when we're taking that measurement, we actually are indirectly assessing the diffusivity of the material and also the permeability of the material. Now, these are the very properties that we need to know as far as performance is concerned. We need to know about its diffusivity. We need to know about its permeability. So hopefully you're beginning to maybe see that if we take this a measurement in situ, we can get an assessment of these other permeation properties indirectly. So what we're doing with some of our work is, this is just one project, we've got a number of projects, but I just thought I would just give you a flavour, is we are embedding electrode systems within the concrete itself, and then monitoring the properties of concrete. We can do continuous monitoring if we so wish. We can take readings every hour, every 5 minutes if we want. But that'll give us then this indication of how this cover zone is performing. And we can monitor the movement of ionic movement through that cover zone. So that's given us an early warning. So we can go in and maybe just simply do a reapplication of silane, surface coating, a surface treatment, rather than doing any major structural repair. So it's given us this early warning. So what we're doing is, say, with our electrode arrays, we're embedding them within the concrete, and we're just monitoring what's happening within this concrete cover zone. Oh, I beg your pardon. So our idea is that we can install sensors within civil structures. We've got a remote monitoring system where we can interrogate remotely from the office setting, and that's what our final goal was. So we're getting some way there. We had a test site set up in Kincardine, just along, not so far away from here, where we had some, I do say that this was carried out with funding from Transport Scotland. We had a number of monoliths which we fabricated with our embedded sensor arrays. Everything was wired back to a central comms box. So we were working on that until we got a phone call from, it was Jacobs, to say, listen, we're putting the approach road to the new bridge at Kincardine through your site. Would you kindly remove these? So we promptly did. Luckily, we had a system set up. We could dismantle this quite easily. So we actually sort of reinstated these back at Heriot-Watt. But that's not what I want to look at. This is another one site that we set up in the Dornoch Firth. And we've got a couple of bits of work going on there. This is, I'll just maybe very briefly mention, these are pier stems which were fabricated from the cut down formwork that was actually used to construct the actual bridge itself. And this is simply looking at chloride ingress into these pier stems. There are 9 altogether. The bottom 3 are actually submerged at this point in time. But we took this opportunity then of developing this site and instrumenting. This is a little schematic of the positioning of these pier stems, of actually getting some samples and instrumenting them and trying to have this remote interrogation facility. Initially, we just had to go up there, pack a van up, and go up and take measurements. But then we developed a remote interrogation system. This is our installation of it up at the Dornoch First, nice dreich October day up in Dornoch. But we managed to get it instrumented. We have our instrumentation. We've got our remote interrogation system. We have, that's just some of the multiplexing units that we've got. This all looks a bit belt and braces, but it can be tidied up. We've got a little battery there, so it's trickle charge from a battery. The battery's charged itself from a solar panel. We're connected to the mobile network, so we can simply dial up and download all the information. And we can trigger readings whenever we want. We could take it, I say, every hour if we so wished. But I mean, deterioration is still a slow process, so we don't need to take them every hour or every day. But we thought we'd just take some results just to show we can get them. These are some data taken from our electrode systems embedded within the concrete cover zone. So that's as a function of time. We were taking readings virtually every 12 hours here. Just some points that that we're confronted with. We're also taking temperature measurements within in the cover zone. There's the conductivity changes. There's the temperature changes within the cover zone. And again, changes in conductivity are also temperature dependent. So we had to get a protocol to actually take that effect out. Which we did. We were able to develop a system. I won't go detail that, but it's actually using the in situ data to develop a correction procedure so we could strip out or take out that temperature effect. So there's the raw data as it's coming in. We do a bit of temperature correction so we can actually correct that out as much flatter so we can correct our data. Again, over that time scale, as I've just shown, it's just 100 days. There's not much happening. It was really just to show that we can actually take these readings now. Again, this is just taking it to a whole extreme. This is, I think we were taking readings every 10 minutes or something like that over a period of 30 days. So you're getting more and more detail as to what's happening within this cover zone. And you can see these fluctuations and that top curve. And again, on the bottom one's the temperature effect. So we can take out that temperature effect to find out exactly what's happening. And so our changes are related to changes due to water ionic ingress and not just due to temperature. So that's some of the data that we've got. So with our work, we can now get a very detailed picture of what's going on within that cover zone. It allows us to give us what I'll call an integrated integrated quality of the cover zone. And we can get, if we wanted, a virtually continuous real-time monitoring. And again, what we're looking at now is looking at retrofitting systems which can go into existing concrete structures. So again, this forms part, I'm not saying it's the the complete package, but it can form part of a maintenance strategy, a monitoring and maintenance strategy. This could be one piece in the jigsaw that we could use to monitor structures. So I'll finish there. I think I've just about used up my time. I want to thank you for your attention. This slide, actually, I thought it was quite thought of. This is actually taken up in Dornoch. This is a Scottish summer, and you can see you've got the beach to yourself up there. So stay in Scotland, don't go abroad. Thank you.